Okay, so what is this? I mean, if you write this exponential down, it's cosine of k 2 pi delta x plus j times sine of k 2 pi delta x. Okay, and if k is equal to 0, I get 1 and 0, right? So the whole lambda is going to be 0. So the lambda would be here for k equal to 0. Well, oh, okay. Now let's say let's say we have k equal to 1 for a very tiny delta x. Where would this be? Well, we know that for a very tiny delta x, cosine is approximately equal to 1. And the sine is very close, the sine of x is very close to x, right? So we actually, for very tiny k delta x, we are actually a little bit up in the imaginary axis, because the cosine is still 1, which means the real part is still going to be 0, and the imaginary part is a little bit. Now, as you increase k delta x, so that k delta x is no longer small, my cosine is starting to get less than 1, which means what? Which means the cosine minus 1 is now negative. And remember, our u is equal to 1, and we have a minus sign here, which means we now get into the positive real axis domain. And that's why the scheme is going to be unstable. And in particular, when k delta x, what's the worst case for k delta x to be? What is the most unstable k delta x? Yes, the most unstable k delta x is for this whole thing to be minus 1, right? And if k delta x is equal to half, okay? So particularly if k delta x, let's see, where is k delta x is equal to half, my lambda is going to be what? It's going to be, we get minus 2 here, cancels, we get 2u over delta x, right? It's actually purely real, it's somewhere here. And if you actually calculate all these lambdas for different case, you're going to see all of them lies in a circle over here. Okay, the most unstable one is 2u over delta x. And what is k delta x equal to half, right? I mean, if you look at the function we are constructing, what is k delta x equal to half? It means my function is e to the j pi times I. Well, for I equal to 0, the value is 1, right? When I is equal to 1, the value is what? What is e to the j pi? Minus 1, right? For I equal to 2, 1 again. I equal to 3, minus 1 again, right? So it's grid by grid oscillation. That's the most unstable error. Look at this. Okay, does it look similar to that? Pretty similar, right? So we get one point up there, another point down here, another point up there, another point down here, right? So of course it's not just that. It's not just that, because we have also other frequencies that grows almost as fast, right? If you look at where is, yeah, if you look at, for example, this lambda, it grows almost as fast. So what you see is not going to be purely like that wave, but like you can see that mode is very significant in this 10 to the 85 error. Okay, so basically this tells you why the solution is unstable and what the instability actually looks like. And it's very useful when you're, for example, you have a code that doesn't work, it blows up. And by looking at how it blows up, it can be actually helpful in determining how can you improve the numerical scheme. Okay, a curious fact over here is that actually, what if a question here is what if u less than 0? So this whole circle I'm drawing is for u greater than 0, right? If u less than 0, well, the most unstable component 2u still is 2u over delta x is actually on the other side, right? So if u is less than 0, all my lambdas lies over here. Then it should actually work, right? So maybe we shouldn't dismiss that too fast. So let's, for example, set u equal to -1. And let's use our forward scheme to solve it. Okay? And let's plot all of this again. Where is it? Oh, by the way, if u is equal to -1, the analytical solution goes towards the left. But still, after it completes one period at t equal to 1, it still should be exactly at the same location. So I'm going to evaluate it. No. Wait. Should I just press enter? Oh, evaluate selection. Okay. Right? So the same thing when u is equal to +1 gives me unstable solution. Now gives me something very similar to the forward, the backward difference operated when u is when u is equal to +1. So maybe there is some kind of symmetry over here. Okay, and I encourage you to do it at home. But like if you plug in not the forward difference scheme but the backward difference scheme over here, you get exactly the opposite conclusion. That is, the scheme is going to be stable when u is greater than 0 and unstable when u is less than 0. Okay, but in principle, what you have is if u is greater than 0, the solution is moving towards your right, and you should be using what? Which scheme? Backward, right? If the solution is moving towards the left, you should be using a forward scheme. So which direction you should bias the scheme depends on which direction the solution is moving, and it's the opposite, right? So if the solution is moving towards the right, you should be using the grid point on the left. If the solution is moving towards the right, you should be using the grid point on the right. So that's actually a common strategy used in discretizing actually any differential equations whose time derivative has a term that is proportional to the first order derivative of the solution. Sometimes it's not obvious that the differential equation actually depends on the first order derivative of the solution, but like through some manipulation, you can find out that if the time derivative is has some proportionality constant to the first order derivative, usually upwinding. Okay, so that's the term for this bias. Is a common strategy used. It's called upwinding. Actually, upwinding, because you think of the movement of the solution as being driven by some wind. If the solution is moving towards the right, it's like driven by a wind that blows from the left. So the upwind direction is actually the left. Right? That's a good way to remember like which direction you want to bias the solution. Okay, a failure to upwind may mean a solution that blows up like crazy. Okay, any questions on this forward versus backward finite difference?